Our next presentation will be given by Dr. Augustine Nti, Power Profiles of Center Distance Multifocal Soft Contact Lenses.
Thank you, Dr. Masak, for that introduction. So my name is Augustine Nti. I'll be presenting our work on the power profiles of center distance multifocal soft contact lenses on behalf of my co-authors. I'm a PhD student at the University of Houston. And these are our disclosures. So as the first speaker mentioned, the prevalence of myopia is increasing globally. And in this graph here from this 2016 paper, it's expected that if current trends continue, then about half of the world's population will be myopic by 2050. And this is a problem because apart from the reduction in vision that myopia causes, it also increases the odds of other vision-threatening comorbidities such as glaucoma, cataract, and myopic macular degeneration. So because of this, several groups are looking into ways by which we can slow myopia progression and myopia prevalence. And one of these ways is with the use of center distance soft multifocal contact lenses. And what I have listed here are just two recent 3-year clinical trials which show the efficacy of center distance multifocal contact lenses in slowing myopia progression. And initially, based on results from animal studies, it was hypothesized that the myopia control effect from these multifocal contact lenses was due to the fact that they were able to simultaneously impose clear foveal vision and myopic defocus. So in this image from this recent paper, you see here that with a single vision contact lens, you have clear foveal vision, but then out in the periphery, the rays of light come to a focus behind the retina, which causes a peripheral hyperopic defocus. And this was hypothesized to be a signal for the eye to grow longer. However, with a multifocal soft contact lens, what happens is, again, you have clear central vision, but out in the periphery, because of the added plus power, the rays of light come to a focus in front of the retina, causing a peripheral myopic defocus, and this was hypothesized to be a signal to slow eye growth. And when you increase the add power, you have a more pronounced effect. However, like this illustration is from the Blink study results, the paper they published. And it was a study in which children, myopic children, were randomized to either a single vision or a plus 150 or a plus 250 add by affinity multifocal contact lenses. And what they saw from that research was that only the plus 250 add multifocal contact lenses was able to slow myopia progression when compared to the single vision contact lens. And also, quite interestingly, they just presented an analysis last week at AVO where they showed only a weak association between peripheral defocus and myopia progression. So what this suggests is that a linear dose response to peripheral defocus does not adequately explain the effects of multifocal contact lenses on axial eye growth. So they propose that probably exceeding a threshold amount of peripheral myopic defocus or some other mechanism other than peripheral defocus, such as contrast or chromatic hues, may be responsible for the significant slowing of axial growth that you see in multifocal contact lenses. But in any case, because of results such as from the Blink study, several clinicians are prescribing these multifocal contact lenses for myopic children. So what we wanted to do was to actually measure and understand the power profiles of these contact lenses. So the purpose of our study was to determine the power profiles of commercially available multifocal soft contact lenses that are being prescribed to slow myopia progression. And we were also interested in analyzing any differences in power profile between different parts of the same contact lens design. So for instance, if you take a bi-affinity multifocal, is there any difference in the power profile between, let's say, a -1 and a -5 contact lens? We selected 3 contact lenses. They were selected because at the time we did a study, they were being used or studied off-label for myopia control here in the United States. So the first was the bi-affinity multifocal D with a plus 250 add. The second was the Proclear multifocal, also with the plus 250 add. And a third was the Natural View multifocal. So here we have the reported power profile of both the bi-affinity and the Proclear multifocal contact lenses. And Here in the center of the lens, you have the distance portion so that the subject is able to see clearly. But as you go out into the periphery, there's a gradual increase in plus power to the edge of the contact lens. And here, this is an image from a patent application by Visionary Technologies. So we think this might be what the power profile of the natural view multifocal is. They produce the natural view multifocal. And here you see that right at the center of the lens, there's a sharp increase in plus power, and then the plus power decreases to create what the company describes as an optical pinhole. But these are manufacturer reported, and we wanted to see what actually is happening in the lenses when you measure them. So we took two lenses in one diopter steps from -1 to -6, and for each power, we measured the two lenses and averaged. The lenses were initially stored in ISO standard PBS for 24 hours before measurements. And for measurements, we used the SHS ophthalmic, which is pictured here. The lenses were placed in a wet cell. The wet cell also contained the same ISO standard PBS. And then we took 3 measurements on each contact lens and averaged. We also measured the center thickness of each contact lens with the iView OCT, and then entered the measured contact lens, the refractive index, and other optical parameters into the SHS ophthalmic software to generate the power profiles. And because we're measuring the power profiles in a wet cell, the power was then converted to the equivalent power in air before analysis. So here's an illustration of the output you get from the SHS ophthalmic. This would be the contact lens, and each square grid here represents a discrete point at which the power is measured. However, we masked the central 0.5 millimeters because with this instrument, you get artifacts within this central portion. This has been reported in other groups that use the same instrument, and they also masked this central portion. And then also because all the lenses were rotationally symmetric, we took the power along the horizontal and vertical meridians and averaged it to generate the power profiles I'll be showing you. And additionally, because these lenses were expected to have very different designs, and because there's no standard on how to report on the add power of multifocal contact lenses, we defined the maximum add power as the difference between the lowest power in the center of the lens and then the most positive power anywhere within the optic zone. And this allowed us to capture the maximum add power irrespective of where it was located in the power profile of the contact lens. And then we used a one-way ANOVA and adjusted post-hoc t-test for analysis. So these are our results. The first one is with the bioaffinity multifocal. Just to orient you, on the y-axis, you have the power, and on the x-axis, you have the radial distance from the lens center. And then each line represents a different power from -1 to -6. All the other power profiles will be of a similar output. And you see clearly that there are 3 distinct zones of the contact lens. First, you have the distance portion, which goes from the center of the lens to about a 1.6 millimeter radius. And then there's the intermediate portion where you see an increase, a sharp increase in plus power. And then there's a near portion, which goes from about a 2 millimeter radius to the edge of the optic zone. And these lines just represent the peripheral curves of the contact lens. What we realized was that for the lower minus powered lenses, like the -1 and the -2, in the near portion of the lens, the plus power continues to increase till the edge of the optic zone. However, with the higher minus powered lenses, like the -6, in the near portion, plus power rather reduces as you go towards the edge of the optic zones. So here the peak plus power is very close to the center of the lens, right here at around 2 millimeter radius. Whilst for the -1 lens, the peak plus power is at the edge of the optic zone of the lens. And we don't know whether this would have an effect on the ability of these different powers of the multifocal contact lens to reduce myopia progression. And again, for the Proclear multifocal, it's also very similar to that of the bioaffinity with 3 distinct zones, the distance portion very close to the center. Then there's a sharp rise in plus power in the intermediate portion of the lens. And then you have the near portion of the lens, where again, for the high minus powered lenses, you see the plus power gradually reducing as you go to the edge of the optic zone. But for the low minus power lenses like the -1, the plus power again increases towards the edge of the optic zone. Again, we have the same phenomenon where the peak plus power for the lower minus power lenses is at the edge of the optic zone, but it's close to the center of the lens for the high minus power lenses. And finally, we have the power profile of the natural view multifocal, which you can see is very different from the first two lenses we looked at. For this lens, right from the center, you see an increase in the plus power all the way out to an about 2.7 millimeter radius. And then the plus power sharply reduces. And then for the lower minus powered lenses, after it reduces, it levels up till the edge of the optic zone. However, for the high minus lenses like the -6, the plus power again continues to reduce. And what this means is that for instance, for the -6, you have a more minus power at the edge of the optic zone than at even the center of the lens. And again, whether this would affect the ability of this multifocal, this particular power to reduce myopia progression is unknown. And I think it would be important for that to be looked at. We also looked at the maximum art power across all the lens powers for each of the brands that we measured. And we saw that the highest art power was with the natural view multifocal, which was around a +0.2. And then followed by the Proclear multifocal, which was around a +1.8 diopter. And then the lowest art power across all lenses was with the Biofinity multifocal with an average of 1.5 diopters. And again, over here in this table, we see that for the lenses, as you increase the minus lens power, so as you go from -1 to a -6, there's a reduction in the maximum art power. And this is consistent across all the three lenses that we looked at. And you have a difference of about 1 diopter between a -1 lens and a -6 lens for the same lens brand. And again, this might affect the ability of the higher minus powered lenses to reduce myopia progression. So to our conclusions, we realize from this work that the power profiles of these multifocal contact lenses depend on the label distance length power and the particular lens design that you are looking at. The highest maximum art power was found with the natural view multifocal, followed by the Proclear multifocal and the Biofinity multifocal. We also saw that the maximum art location varied based on the distance lens power for the Biofinity and the Proclear multifocals, but was consistently at 2.7 millimeter radius for the natural view multifocal. And we think it's important for research to be done to understand whether the effects of the maximum art power, the maximum art placement, whether it's close to the center of the lens or it's closer to the edge of the optic zone, and the distribution of the art power within the lens influences the ability of a lens to reduce myopia progression. So I'd like to thank Dr. Masaka and Dr. Hastings. They were very instrumental in helping us take these measurements. We've published these results in a recent paper, and you can just scan this QR code to read that paper. And if there are any questions, I'll take them now. Thank you.
Great. I think we have time for 1 or 2 questions. Augustine, I'll start with one. You had showed that the power profile is slightly different for the high negative lenses versus the less negative lenses. Like the -6, that power in the periphery tailed off. Is that a fact, like a manufacturing issue, or is it by design for some like visual function?
That's difficult to tell, but because it's consistent across all the 3 different designs that we looked at, it's probably because of negative spherical aberration, where as you increase the label distance lens power, you have more negative spherical aberration, and then that causes that reduction in plus power you see for the high minus powered lenses. So probably in manufacturing, they might need to control for this so that you don't see that tailing off in the higher minus powered lenses.
Thank you. I think Jim Schwegerling also has a question.
Yeah, so my understanding with the natural view lens was that it actually has like a very small region that has the power of the lens, and then outside of that, it has very high spherical aberration that basically blurs everything going through the periphery of the pupil. So it's acting more like a pinhole effect than having like a true add power like the other two lenses that you described.
Okay, okay. And also because we maxed the central 0.5 millimeters, if that's where the distance bar is, then we couldn't see it in our measurement, yes.